The James Webb Space Telescope JWST has unveiled a stunning phenomenon. Beams of light seemingly emanating from a region that resembles a distant city glowing brightly. From tens of light years away, this astonishing discovery has reignited speculation about the existence of extraterrestrial civilizations, focusing on Proxima Centauri b, the closest known exoplanet to our solar system. JWST detected unusual bursts of radiant light. Could these emissions be signs of an intelligent alien society? The world is watching closely for more revelations. For decades, both scientists and the public have been captivated by the possibility of life beyond Earth. Any indication of extraterrestrial presence stirs widespread excitement. But a pivotal moment arrived when the James Webb Telescope delivered its most compelling evidence, yet suggesting the existence of life somewhere in the universe. While scanning the depths of space, this powerful instrument detected luminous patterns on a remote planet that resemble artificial city lights, sparking intense scientific interest. This may be the long-awaited breakthrough, a sign of intelligent beings creating and sustaining a civilization far from Earth. The light appears to originate from Proxima Centauri b, just over 4 light years away. The revelation has left NASA engineers astounded, prompting the question, how long have these lights been shining in the cosmos before our instruments became capable of detecting them? Astronomer David Kipping of Columbia University noted the planet's complexity, especially in how it interacts with its host star. Unlike typical rocky planets that absorb starlight and emit infrared energy uniformly, Proxima Centauri b behaves differently due to its unique orbital relationship with its star. This finding underscores JWST's critical role. Its ability to detect infrared wavelengths was essential in observing the planet's peculiar emissions and assessing its atmospheric conditions. Scientists plan to continue studying Proxima Centauri b using JWST's advanced instruments, focusing on its atmosphere and evaluating whether it could support life. Unlike many telescopes that struggle with the faint glimmers of distant objects, JWST is optimized to detect subtle infrared signals, making it ideal for confirming whether the light on Proxima b's night side is truly artificial. Proxima Centauri b experiences a dynamic exchange of energy with its star. Like Earth, it undergoes cycles of day and night, though the temperature swings are far more extreme. If the planet has an atmosphere, one hemisphere may be scorched by constant daylight, while the other remains frigid in perpetual darkness. Such dramatic thermal variation provides crucial clues about the planet's atmospheric structure and chemistry. Using its infrared capabilities, JWST can measure the heat emitted by the planet, helping scientists determine whether it has a stable atmosphere. Notably, JWST's observational schedule aligns with Proxima Centauri b's orbit, which completes a cycle every 11 to Earth days. If the planet does have an atmosphere, scientists will begin analyzing its chemical composition to assess its habitability. Detecting molecules like oxygen, methane, and water vapor could suggest conditions suitable for life. This requires studying the light that filters through the planet's atmosphere, a delicate yet vital process. Although JWST is primarily designed to detect compounds like water vapor, carbon dioxide, and methane, it is less adept at detecting free oxygen, a key biosignature. Still, it can detect ozone, a reliable proxy for a breathable atmosphere. As researchers continue examining the data, the search for life becomes more focused and methodical. JWST is currently best suited for nearby exoplanet targets. For deeper atmospheric analysis, astronomers are looking ahead to ground-based observatories like the extremely large telescope L, expected to begin operations in 2027. The L will offer even more detailed atmospheric assessments, complementing JWST's findings. Together, they will allow us to explore exoplanetary environments with unprecedented precision. Even with its limitations, JWST remains an essential tool in this grand search. Future space telescopes are expected to reduce the overwhelming brightness of stars, making it easier to observe the faint reflected light of orbiting planets. Much like shading your eyes to see something in the sun, these advanced instruments will use techniques to block starlight, enhancing our ability to study planetary surfaces and atmospheres. One promising approach involves coronagraphs devices, built into telescopes that block a star's light, while allowing the dim glow of planets to pass through. These instruments manipulate light waves to drastically reduce stellar glare. Another innovative solution is the Starshade, a massive flower-shaped spacecraft designed to fly tens of thousands of kilometers in front of a telescope, blocking starlight before it even enters the lens. This technique could be particularly useful for studying planets in habitable zones where liquid water might exist. However, these technologies demand extreme precision. Aligning a star shade with a telescope over vast distances must be accurate to within a fraction of a millimeter. These systems must also be compact, power efficient, and durable enough to survive the harsh conditions of space. Despite the technical challenges, the rewards are enormous. If we succeed in studying exoplanet atmospheres in detail, we may uncover biosignatures, chemical markers that suggest life. The presence of oxygen, methane, and water vapor in specific proportions could point to biological activity. Researchers are also working on capturing clearer images of distant planets. Future telescopes may feature adaptive optics that correct for distortions, offering sharper, high-resolution views, combined with light-blocking technologies. This would enable scientists not only to detect distant worlds, but also to map their surfaces and track weather systems. Such capabilities would mark a revolutionary leap in our understanding of the universe. As space exploration continues to evolve, the search for extraterrestrial life becomes increasingly precise and hopeful. JWST and its successors will remain at the forefront of this effort. Every new observation brings us closer to answering the most profound question: are we alone in the cosmos? The light detected around Proxima Centauri b may be just the beginning of a transformative era in space science. Though the Proxima system has long been studied, definitive evidence of artificial illumination had remained elusive until now. This new data significantly increases hopes for future contact with intelligent life. More than just a scientific milestone, this discovery captures the public's imagination and inspires future generations to look beyond Earth. As JWST continues its mission, it will analyze planetary atmospheres, track their chemical profiles, and search for elements essential to life. Its ability to detect atmospheric compounds like methane and carbon dioxide in key ratios is unmatched, offering insights no prior instrument could provide. The journey toward discovering life beyond Earth has reached a turning point, and JWST stands at its center. One of the most intriguing features of Proxima Centauri b is its location within the habitable zone of its star, the so-called Goldilocks zone, where conditions may allow liquid water to exist. This region, not too hot and not too cold, is considered essential for life as we know it. Discovering a planet in this zone, especially one showing possible signs of artificial illumination, has become a top priority for astronomers. Beyond identifying potentially life-supporting worlds, upcoming missions aim to explore the intricate relationships between exoplanets and their parent stars. Some exoplanets, such as Proxima b and Tau Ceti b, are thought to be tidally locked, meaning one side always faces the star, while the other remains in eternal night. This configuration creates extreme temperature contrasts that dramatically affect the planet's climate and atmospheric behavior. Understanding how such extremes shape weather patterns and atmospheric circulation is vital for assessing a planet's ability to support life. Technological advancements in starlight suppression, such as coronagraphs and starshades, are revolutionizing our ability to study these distant worlds. Without these tools, the intense glare of a host star would drown out the faint reflected light of its orbiting planets. By blocking starlight, these innovations enable astronomers to detect the faint signatures of exoplanets, revealing crucial details about their weather, surface conditions, and biological potential. Another exciting frontier is the emergence of high-resolution direct imaging. Paired with adaptive optics and sophisticated light filtering methods, this technique may soon allow astronomers to capture images detailed enough to show oceans, continents, clouds, and even seasonal changes on alien worlds. Such imagery would represent a groundbreaking leap in our understanding of planetary environments, enabling us to go beyond detection to characterization. As we continue our journey through the cosmos and refine our detection tools, the role of the James Webb Space Telescope and the next generation of observatories becomes increasingly vital. Their contributions bring us ever closer to answering one of humanity's most profound questions: are we alone in the universe? Its remarkable infrared sensitivity enables it to detect even the faintest emissions from exoplanets, analyze atmospheric layers in detail, and identify potential biosignatures, clues that can suggest the presence of life. As technology continues to advance and our collection of cosmic data grows, Humanity stands at the edge of discoveries that could dramatically reshape our understanding of our place in the universe. The possible detection of artificial light or an urban-like glow on Proxima Centauri B, our closest known exoplanet, could mark the beginning of a transformative new era in space exploration. This pursuit is not just about gathering scientific evidence. It also sparks profound philosophical questions. What if we are not alone? How would contact with another intelligent species alter the course of our civilization? The intrigue surrounding Proxima Centauri B underscores our innate curiosity and desire for meaning beyond Earth. Future observatories, both in space and on the ground, will continue to push the limits of what we can observe. With enhanced light filtering, sharper imaging, and more powerful spectral analysis, we'll be able to explore alien atmospheres with unparalleled clarity. Beyond identifying biosignatures, these tools may eventually uncover technosignature signals or structures that point to the existence of advanced civilizations. With every mission and each fragment of incoming data, we move closer to answering one of humanity's most enduring and profound questions. Are we truly alone in the universe?